Okay, picking up in part 2 here, we just have to figure out an actual number for this. So if you actually wrote this out as this divided by this with a division sign instead of the bar, when you divide, you multiply by the reciprocal, so that would actually become 5/4. What would happen is that 5/4 would cancel with this one. So really it's 1 minus 1 over 5 to the 10th divided by 4, but I can't guarantee those are always going to be the same numbers. So here's how I did it in the calculator. So I started on the inside, 1 minus 1 over 5 to the 10th. 5 to the 10th is huge. Okay, it's a super big number, but it makes a really small fraction because it's on the bottom. So you're basically really close to 1, except for a few little things out here. Now I divided it by 0.8, which is 4/5. So if you don't use correct parentheses when you're dividing by fractions, it may not be right. And then I took that answer and I multiplied it by 1/5. So what you really get out of this sequence as you do the first 10 terms is you get 0.24999 on and on. So if you did the 11th term, the 12th term, the 13th term, it's really only going to add very small amounts in here. So basically what we would say is, you know, this thing approaches 0.25. Okay, it's a little taste of calculus for you guys there. So as, you know, we add more and more terms, this thing's going to get close to a quarter. Okay, 0.24 with a bunch of 9s is basically 0.25. Okay, so that's the sum of that sequence. Okay, good. Now, if we look at this, so if we want to sum a geometric series, okay, we know what the sigma means. We're starting at a k equals 1. Notice we're going to infinity. Okay, first term ratio to the k minus 1. It's the same thing as us using n minus 1s. It's just in the summation notation. There's two different ways that this can happen. So what happens if you let n get really big? Okay, last one we stopped it at 10. But we talked about if it kept going to infinity, it wouldn't change our answer. It's just going to get close to 0.25. Now, if r is big and you keep adding bigger and bigger numbers, what does the series approach? So for example, let's say I gave you the series 4 plus 8 plus 16 plus 32 plus 64 and so on. Okay, clearly the rate is a 2. We raise it to the n minus 1. So if we sum this thing up from a 1 to the infinite term of 4, 2 to the n minus 1, what's going to happen? Okay, 4 plus 8 plus 16. Okay, we're starting to get bigger and bigger, but eventually we're going to reach a point where you're doubling 1,000, you're doubling 2,000, you're doubling 1,000,000. Okay, we would say this goes to infinity. Okay, think of it as money. If you get $4 plus $8 plus 16, keeps adding, eventually you're going to have infinite dollars. So obviously we'd have to work on the notation, and you guys will look at that if you do take a calculus class. But if your rate is big, in this case, you know, a 2 or even a 1.5 or even, you know, a 6, 7, whatever, they're going to sum to infinity. If the numbers get bigger, the series is going to go to infinity. Now, what happens if you let n go to infinity where the rate is small? So like we had in that last problem where the rate was, or the ratio was 1/5. That's a small ratio. Okay? After a point, you aren't really adding much to the series. So for example, 1 plus a half plus a fourth plus an eighth. If you wanted an equation for it, okay, clearly we're cutting this in half every time, raised to the n minus 1. There's your formula. So we're trying to sum this up from 1 to infinity of 1/2 to the k minus 1. Okay, so what would happen to this? You go to your calculator. and you start adding these up. Okay, 1 plus a half takes us to 1/4, or to 1 1/2. You add a 1/4 to it. You add an 1/8 to it. You add a 16th to it. You add a 32nd to it. Okay, you add a 64th. You add a 128th. Okay, you're going to see we're not making much of a dent, whereas before, we were adding 50 cents, a quarter, an 1/8 of a dollar, 1/16 of a dollar. Now we're not really making much of a dent at all. Okay. So if we kept going and we added in this 1 over 1024, the next one would be 1 over 2048, and we add that in there, it's not going to do anything to this. Okay, didn't change it at all here. This 2 went to a 3. Okay, if you're thinking about money, that place doesn't even matter. So some magic calculus happens, and you come out with this equation here. So if the rate is anywhere from -1 up to 1, so a fractional ratio here, okay, obviously it can't be a 0, then here's what happens. It's just the first term divided by 1 minus r. Okay, this is only if the rate is small. So if you're adding less and less and less each time. If you're adding more and more and more each time, this thing goes to infinity. So if we had that last example there, we would simply say first term was a 1, rate was 1/2, this thing goes to 2. Look at what we had in the calculator. We keep adding more and more and more stuff. We're already at $1.99, so we just need to change that last 99 into $2. So we say this thing approaches 2. Okay, last little problem here. We want to find the sum of this. So it's going 3 plus 6/5 plus 12 25ths. If you want to continue the pattern, it looks like 3 over 1, so the top is doubling, 3, 6, 12, 24, and the bottoms are multiples of 5, so this should be 24 plus 125, and this would keep going. Okay, all we need again, because these are getting smaller and smaller and smaller, is we need this formula right here. So we already have the first term as a 3. I just need that rate, or the ratio. So I need to find the ratio. So I need to divide the terms by the previous term and figure out what happens with these. So I just did the first two here. We can't always assume just because the first two are a constant ratio that they all will be, but because I'm giving you the problem and asking you to sum it, you can assume these are geometric. So we found the rate is 0.4, which is the same thing as 2/5. So if we plug in the 0.4, that's an easy calculation for you guys. So 3 divided by 0.6. But what happens if we actually did plug in the 2/5 there? So if you're given a problem where they gave you the rate as a fraction, you got fractions hidden within fractions. We haven't looked at one of these in a while. Clear the 5s right out of there. And either way we do this, we'll end up with 5. So as this guy goes to infinity of this equation right here, or that series, these will all sum to 5. So we started with 3 plus 6/5. We're already at 4.2. So everything we add afterwards is just slowly, slowly, slowly getting us closer and closer and closer to 5. Okay, so there's a quick little lesson on geometric series and sequences. Make sure you guys have your formulas down. and bring your questions to class.